Hello, everybody. So my title of my talk is IP and Optical Convergence, Opportunities and Challenges in a New World of Coherent Pluggable Transceivers. I work at an American company called Infinera, and we work at the bottom of the OSI model in the real basement with the optical technology that sends light down the fiber, connecting two routers together and letting the traffic pass with no error. But there's a lot going on to make that happen. As you know, the internet is something very different today than it was 20 years ago. Internet grew in Sweden, over in Stockholm, Jakob, over the last 20 years, and it did in the rest of the world as well. And there's a lot of work that it's taken to make that happen at all layers of the OSI model, the whole stack, right? And I'll give you a little idea of what's going on at the bottom of the stack there. So my employer, Infinera, we've been around since 2001. We build optical transport solutions, optical transport networks for a variety of different segments of the network, from data center interconnect on the right, shorter links connecting data centers within a metro. And at the other extreme, we make sure that capacity traffic can flow through submarine networks, so subsea cables across the Atlantic or even Pacific Ocean. Then on the terrestrial side, we build long-haul networks, metro networks, and even access networks or networks for mobile network operators. So it's all about connecting people and applications to the cloud and to each other. And we have to do this in a very seamless fashion so people above us don't even notice we're there. If you're operating a router, you probably just want to be able to, ping the far end router and have it respond, right? But to make that happen over a long link, there's a lot going on. So you can actually view the optical transport network similar to other types of civil infrastructure, like roads or railroads. If you take the road analogy, the equivalent of the actual pavement or the road is the optical layer, which is the fibers, the transmission fibers that are laid in the ground, amplifiers that are used, because the light goes down the fiber, it's attenuated, and after about 80 kilometers or so, it's time to amplify it again so you can reach the next city. So there are amplifiers, there are also filters to keep different wavelengths apart. I'll talk more about that shortly. And things called ROADMs that are advanced filters that can kind of steer the light in different directions. And on this road, right, if you have a road in a city, right, you have different kind of vehicles. It could be cars or trucks driving on that road. And the equivalent in our transport world, is you have some type of chassis, like an optical transport chassis with different cards in it. But to power the transport vehicle, the car or the truck, there's an engine. And the engine in the optical networking side is made up of lasers, modulators, photodiodes, little optical components that can either produce light, turn it on and off, change the phase, so the timing of the light, or combine it, do things to it, or detect it. There's also digital signal processors. That's something we're really good at Infinera. We've been building for about last 10 years, and the packaging to put it all together. And, networks are built at different scales. This is just to illustrate, right? You have long haul networks with typically like an IP backbone in a larger country. Will actually have the links between the core routers will be quite large. It can be 1,000 kilometers or 1,500 kilometers if you look at the North American backbone. Metro networks are shorter, where traffic is aggregated from the access networks into the core site. And basically, all of this is fiber in the service provider networks. Fiber optics underpin in all of these networks, with the exception of the last mile in some cases, whether it's wireless, like 5G or 4G radio access networks, or older copper networks, DSL or coax. Everything else is fiber in between, and this is what we build the technology for at Infinera. And in many cases requires high performance optics because there's just so much traffic going through the internet these days. So, if you take a fiber cable going between two cities, right, a typical simplified type of fiber optic transceiver is basically just a light switch that's on and off, like Morse code, right? You blink the lights at one end, light goes through the fiber, comes out the other end. There's something more advanced, been around for about 30 years, called dense wave division multiplexing, where you take lasers of different colors and you combine them into one transmission fiber. So you can get much more capacity into the same fiber. And on the other end of the cable, you split it out again into different receivers. So this way you get a ton more capacity into the fiber. And skip this slide. And I would say this basic way of just turning light on and off, that's like, it's called amplitude modulation, right? Like on a radio, AM radio, where the signal is either, you kind of turn it on and off. That's a very basic way of optical communication. So about 10 years ago, there's a new type of optical transmission introduced called coherent transmission, where it's not just amplitude modulation, it's also adjusting the phase of the signal. So similar to frequency modulation, quite similar to frequency modulation, it's using the timing of the pulse and not just the amplitude of the pulse to send information. The amount of capacity that we can now pass on fiber optic cables is tremendous, right? So if you look back in 2000, a typical, state-of-the-art optical transport system had 40 colors of light going through it, each carrying 10 gigabits per second of traffic. And that's just grown tremendously, right? So with the introduction of this coherent transmission with both phase and amplitude information about 10 years ago, the amount of capacity on a fiber has just exploded. You can see here that 40 times 10 gig or 400 gig on a fiber pair in 2000, we're now up to close to 100 terabits on the latest generation optical transport systems. And this is really what's allowed the internet to grow as much as it has. This is why it's so much cheaper to place a call across the Atlantic now than it used to be, because service providers don't need to light up so many fiber cables, right? They can use the existing fiber cables and get a tremendously more data on those cables. And roughly what's happened is that the amount of capacity per fiber has grown 30% per year, so 200 times. So 30% a year for the last 20 years, factor of 200, right? So this is pretty cool. And what's also happened is that the size of the systems have gone down tremendously. So I joined Infinera in 2001, and we actually introduced this. This is a little picture of our chassis our first product called the DTN, which at the time it was introduced in 2004, late 2004, where our first shipment was a tremendous success. It was revolutionary. It was 20 RUs high with 400 gig of capacity in it, some switching, and we sold a lot of these and created, in 3 years, we became the #1 in the market worldwide and drove a successful IPO for Infinera. So I'm suddenly starting to feel quite old, because state of the art now, today, this year, and this is a picture of a product that we're releasing now, that we're shipping now, called XR Optics. It's a little pluggable transceiver, QSFP-DD form factor, it has 400 gig of capacity, and you can see the size is now something that you can hold in your hand, right? The size of a pen, and it uses 0.06 watts per gigabit per second of transmission, compared to 4 watts per gig back in 2004. So, it's just tremendous how the industry has moved along. And what happens now, right? You have what's really used to be a whole, like half a rack chassis that's the size of a pen, right? It's a whole system in a plug. What can you do with that, right? So these pluggable transceivers, it's not just Infinera building pluggable transceivers, coherent pluggable DWDM transceivers. They're available from others as well. But what's happened is that they used to be bigger and now they got smaller and smaller. So you can have a coherent pluggable QSFP-DD in the same, envelope as a short reach client optic that's normally used to connect, two adjacent router ports. So what happens is that more and more of the links in the network, not just, are becoming these pluggable transceivers and not big old systems. So, and that is a tremendous shift that's starting about now, right? This is the first time in the industry, people have talked about this for a long time, that you can take a full DWDM system and collapse it into something small enough that it can be deployed in a lot of other places. And to do that, a couple of things need to happen. First of all, you need to be able to have a transport interface that's good enough to interconnect routers in different cities in an IP backbone. So, and not just in a small country, like I'm currently in Denmark, in Copenhagen. Denmark is not very large geographically, but you want to be able to do it, let's say, in the US. So state of the art today for coherent QSFP-DD pluggables is to run 400 gig of traffic from a DD port across 2,400 kilometers, right? So that's far enough to basically be usable for most IP interconnect links. And you want to be able to do that in a router, like stick it into commercially available router and just have an interconnect through an optical transport network, as if the routers were situated next to each other. So that's possible to do today. There's also other new things, cool new things going on in transceivers where you can start doing things with DWDM that wasn't possible before. So for example, have one 400 gig plug talk to many 100 gig plugs. So you may be familiar with like breakout cables, DR4s, for example, where you have one 400 gig router port, which is configured to have 400 gig MAC, and each MAC coming from a different destination. So you do kind of port to port here. And now we can do that with DWDM pluggables as well, but over a much longer distance, so hundreds of kilometers. So you could have different types of devices hosting coherent pluggables and interconnect those devices over distance. So here, for example, is a demo we had at OFC where we had a Juniper router hosting an Infinera QSFP-DD. Another, this is an Infinera device host, but also an EdgeCore box and a Sumitomo Electric switch, all hosting coherent pluggable optics and talking to each other. And, when you're doing this, when you start taking a device that's, like a whole optical transport system, and you start plugging in it to devices like routers or switches, or even for edge compute applications, could be a server, like a network interface card. You start getting some new interesting issues, because all of a sudden, you still need to manage that transport. There are a lot of analog parameters happening in the fiber optic world. that people operating routers or servers or even radio units in a radio access network, they don't want to know about those parameters. So there's still quite a lot of work to be done there. So for example, if you take this Juniper router, for example, so if you want to use one of these coherent transceivers, you need to be able to talk to it. You need to be able to set things like the operating wavelength, operating output power, modulation format, a lot of little things. And the way that's done today is that these QSFP-DDs, basically all QSFP-DDs by standard, have a little electrical interface, an I2C bus, it's called. It's two wires on the back of the plug here that are dedicated to communication. And it's not very sophisticated, but it's very robust. This I2C standard is an industrial old standard. It's very, very good for connecting all sorts of devices at low speed. And so the router has to know how to talk to the device over this I2C bus. And it also has to understand how to configure a lot of things in a very, I would say, complicated fashion. So if you want to set the frequency, for example, or output power, you have to look at this memory map, right? There's a whole bunch of memory pages of where different things are stored. So you can read out like bit by bit where in memory you can configure these things, and then you can set them as well. So if you want to set the output power to a milliwatt or 0 dBm of light coming out, you have to know like how do you convert that into into a signed in 16-bit integer, and then you have to go to the right offset in this map and write those things, and then commit that somehow, send it down, and then hopefully it will work, or it will work if you do the job right. And then this map changes over time because new features are added. So it's not really plug and play. And that's the challenge because there's a lot of evolution. I showed you how the capacity per fiber has grown tremendously, right, over the last 2 decades. And there's a lot of R&D, there's a lot of innovation in this space, which drives a lot of changes in these memory maps, which drives a lot of changes in things like router software to keep up so that service providers can leverage this new innovation that's ongoing, right? The new and better products from the industry. So, there's got to be a better way to do that. And that's something that we put a lot of effort into with a lot of other service providers. And we're actually, there's a smart way to do it where we leverage, you kind of look around how other industries have solved the same problem. If you look at telephony, remember when you had a phone in your home? I mean, this is a cordless phone. I never had one of those when I was a kid, but if you want to make a phone call, you had to go to your home to a dedicated room, probably and dial things, right? And over time, wireless connectivity has gotten a lot more accessible. So Ericsson, Swedish company, they launched this hotline phone sometime as an NMT system back in the 80s, I think. Very, very heavy thing, mounted in your car, needed a lot of power, even in standby mode. Then we got mobile phones. And actually today, if you need wireless connectivity, there are these little chipsets, right, that you can buy and put those pretty much anywhere, and it doesn't need much power. And those chipsets can go in various things like lawnmowers or drones, right? Can have a little wireless chipset so you can see if you're flying it far away, you can still see where you're flying, I guess, and even smart water meters can have a little wireless chipset. And what's really nice about this whole wireless industry is that they've done a great job at abstracting all the complexity to the end user. So the lawnmower, this robotic lawnmower, right? You can just, you basically just, the lawnmower doesn't have to know anything about which base station it's connected to. It doesn't have to know what frequency to talk to dial in at, right? Or time slots to listen to. That's all. It's getting connectivity. That's all it knows. I mean, maybe you have to install a SIM card, but even those physical SIMs are even not required anymore. They're eSIMs. So basically, the hosting device, the consumer of the connectivity, doesn't need to have any special domain knowledge. It's just getting the connectivity it needs. And this has driven a tremendous explosion of different new, wireless things, whether it's sensors to sense if you watered your lawn or all sorts of things, right? And what's happening in our industry now is, people are starting to think about, or actually actively thinking about, how can we use these coherent smart transceivers in our routers, for example. That's a big topic, IP over DWDM. And the problem becomes that, while you can do this, these plugs exist, you can put them in your routers, you can even manage them with this. I told you about these memory maps, etc. It's pretty clunky and complicated. And people who know transport, DWDM, and people who know IP, or it's like oil and water, right? It's two different layers in the OSI model, each with a ton of complexity. And the whole point of the OSI model is that you shouldn't have to know more than your own layer, right? You can just count on the layer below you to work. So, while, some operators, service providers, they're actually combining their IP and optical team. That's the whole concept of IP optical convergence. But it comes with a lot of operational challenges. And if you start thinking about all the new places you could put this smart optical transceiver, it's not going to be scalable, because it's not just routers that could consume fiber high capacity fiber optic interfaces. It's also things like radio units or baseband units in radio access networks, optical line terminals in access networks, or network interface cards, and potentially a lot of other things. Probably not toaster ovens, but maybe something at your home, your TV, who knows? Holographic TV may drive a lot of bandwidth. So we think that there's a different way to do this, where we try to take a cue from the wireless world, where they've done a fantastic job at abstracting a very advanced and complex transmission into something that the user doesn't see. So the idea being that the optical transceiver, the smart coherent optical transceiver, can be plugged into a device like a router, which is able to do things like manage the SerDes lanes. Is this a single 400 gig eMAC, or is it 8 times 50 gig E, or what is it? And it can turn the port on and off. And other than that, it just provides fiber connectivity. And then all the optical parameters are managed by the people who know optical parameters and are experts at that. So the DWDM team, the transport team, the fiber optic team, who manages the fiber optic network already. And this is a much cleaner way of doing things. And it turns out it's actually not it actually fits much more nicely into things like SDN hierarchies. So people talk about, a lot of people talk about SDN these days, right? Where you have this hierarchical structure with an orchestrator up top, an application domain controller, a packet domain controller, and a transport domain controller. And each domain controller controls its own set of equipment. So the packet domain controller controls the routers, application domain controller controls the servers, transport domain controller controls the transponders. And of course, the line system, so the fiber amplifiers and things like that. The issue then is that when if you get, I'm going to step through some of the animations here. If you have a pluggable, step too long. If you take your optical interface and you put it directly in your router and launch it into your fiber optic system, optical transport system, all of a sudden your packet controller has to start configuring transport parameters. And this becomes very clunky. You don't want your packet controller have to know this and send things up to the orchestrator, which sends it back down to the transport controller. So this is an industry-wide problem that's being looked at in a lot of places. What you want to be able to do is have the transport controller directly talk to these transceivers, optical transceivers, launching the wavelengths wherever they're deployed. So whether they're in this router here or even in the server, you want the transport controller to address these directly. And with a smart optical controller, you can actually do this. And again, taking a cue from other parts of the industry, so Internet of Things. Internet of Things is basically millions and millions of devices with very low power envelopes, some of them even running on battery, right? That have to be controlled in a secure fashion. And this is similar, right? So pluggable transceivers, they don't have a whole lot of power, and they need to be controlled in a secure fashion, managed in a secure fashion. So we've actually worked to create an MSA specification for precisely what I've been talking about, being able to manage, keep life easy for the layers above. And this is something that's realizable in smart optical transceivers to make IP optical convergence much easier. So we created this MSA working group called OpenXR Forum, where this has been worked out with a large number of operators, also some equipment providers and component manufacturers, to make, and we're hoping to get this standardized over time to basically create this vision, right? That, to summarize, so optical transport is moving into new devices, and it's enabled by a shrinking form factors and power envelopes, which means that you can now simplify your hardware architecture. You don't no longer need a separate large chassis just to handle your optical transport. You can basically collapse that chassis into a single plug and put that in almost any type of device that needs high capacity connectivity, just like you can with the little wireless chipset. This is in essence a fiber optic chipset, right? That can be plugged in wherever you need it, and to deliver high capacity service virtually everywhere, anywhere, and save a lot of space and power in the process. And however, this won't happen, right? Unless there's a way to manage these things. You can't expect that all these end users of high capacity services have that they need to know how that's realized, right? To them, it's just capacity that you want to make available, just like the wireless world has done for decades. So it's possible to do the same thing in fiber optics. We can just quickly leverage all the protocols and software stacks from IoT for the whole management, and that's something that's being done and is available to the market now. So I hope that's the conclusion of my talk. I hope you've learned a little more about what's going on at the basement of the OSI model, fiber optic communication, and how we can help you basically keep the bits flowing and make it possible to ping that router on the far end, on the other end of the fiber, and get a response, right? So if you want to learn more about smart coherent pluggable optics, you can go to this website here or send me an email. Over to the studio.